Hello, everyone. As we go about life each and every day, we see objects that move a lot less quicker than the speed of light, in which Newtonian mechanics is formed by this type of motion. Although, when talking about speeds close to or the speed of light itself, relativity comes to play. With relativity in modern-day society, we have been graced with the GPS and nuclear power plants. Galilean relativity. In general, a physical event is described through a frame of reference. In terms of Galilean relativity, the laws of mechanics are always the same in all inertial frames of reference. The law of universal gravity and equations of motion under constant acceleration are obeyed in both scenarios of the figure, as you could see. No mechanical experiment can detect any difference between the two inertial frames. The only part that can be detected is the relative motion of one frame with respect to another, such as in the figure. Galilean space-time transformations. If an event or physical phenomenon occurs and is observed by an observer at rest in an inertial reference frame, the event's time and location can be determined through these calculations. For an example, referring to figure 39.2, we see that there are two observers which go by S and S prime, and an event occurs at point P, along with four coordinates, which are X prime, Y prime, Z prime, and T prime, which are equal to the equations below. These are known as the Galilean space-time transformation equations. If there is a displacement of magnitude dx along the x-axis, a time interval dt as measured by an observer, which we know as s, then we arrive at the new equations below, which is the Galilean velocity transformation equations, where u prime of x and u of x are x components for the velocity of the particle measured by the observer s and s prime. Speed of light. First off, Galilean transformations do not apply to the speed of light. Observers fixed on the Earth can take the view that they are stationary and that the absolute ether frame containing the medium for light propagation moves past them with speed v. Determining speed in this situation is similar to determining aircraft traveling in a moving air current or with the wind, in which we say if light travels along the x-axis and an observer moves with velocity along that direction, the observer measures the light to have speed c plus or minus v, depending on the direction of travel of the observer and the light. According to Galilean relativity, the speed of light should not be the same in all inertial frames. To resolve this, the concluding statements are the laws of electricity and magnetism are not the same in all inertial frames, or 2. The Galilean velocity transformation equation is incorrect. The Michelson-Morley experiment. This was designed to determine the velocity of the Earth relative to that of the hypothetical ether. This experiment was used to determine and detect the ether wind. Negative results came from this, which were that the experiment contradicted the ether hypothesis, and it demonstrated that it was impossible to measure the absolute velocity of the Earth with respect to the ether frame. Einstein, however, had another concept that developed light to be an electromagnetic wave, which requires no medium for its propagation. This Mitchell-Morley experiment could be seen in figure 39.4. For the Michelson-Morley experiment, when referring back to figure 39.4 on the previous slide, calculations can be found for the time difference, path difference, and the shift for this experiment. In order to find the time difference, you would have to subtract the time of arm 2's rotation by that of arms 1, which results at approximately length times velocity squared over the speed of light cubed. And the path difference can be defined as twice the length times velocity squared over the speed of light squared. And the shift would be the same equation as the path difference, except 1 over lambda would be multiplied into that equation. To remove a lot of the difficulties that arose with Galilean's way of dealing with relativity, Einstein simplified it and based a special theory of relativity on two principles. His first principle states that laws of physics must be the same in all inertial reference frames. And then the second is the constancy of the speed of light, states that the speed of light in a vacuum has a speed of light c is equal to 3.00 times 10 to the 8 meters per second. With these principles, we can come to agree that the relative motion is unimportant when dealing with measuring the speed of light. Consequences of the special theory of relativity, simultaneity, and relativity of time. When it comes to simultaneity and relativity of time, I like to imagine someone observing lightning close up and another observer from a distance in which they think the event happens at different times, which causes them to hear thunder at differing times. In this figure 39.5, we see that there are two observers, O, who's stationary in between the ends of the train cart for each event, and O prime, who's moving in which observes different times that the lightning struck. From this, Einstein's thoughts demonstrate the observers may disagree on the simultaneity of two events, and it just depends on transit time of light to observers. Time dilation. In order to show that observers in different inertial frames can measure different time intervals between a pair of events, we can consider the figure shown. The proper time interval is the time interval between two events measured by an observer who sees the events occur at the same point in space. O prime. Time dilation can be generalized as all physical processes are measured to slow down when those processes occur in a frame moving with respect to the observer. O. One good example of time dilation is the observation of muons and their possibility of coming to the surface of Earth. You can calculate the change in time and the proper time interval through the equations below. The twin paradox. An interesting concept dealing with time dilation is the twin paradox, in which one can understand as there was a pair of twins that were the exact same age, and one went out on a mission to a different planet and came back aged, but not as aged as the twin that remained on Earth. A prime example of this can be seen in the movie Interstellar. Length contraction. The length of an object measured by someone in a reference frame that is moving with respect to the object is always less than the proper length. The proper length is the length measured by an observer at rest relative to the object. An example of this length contraction is also observing a muon approaching the speed of light. An Earth-based observer measures proper length, while the observer in the muon's reference frame is the proper lifetime. The formulas that express these are length is equal to the change of time over gamma, which we defined in the previous slide, and length is also equal to proper length times 1 over gamma. Here is a recap of what we have learned. We have went over the principle of Galilean relativity, the Galilean spacetime transformations, speed of light, the Michelson-Morley experiment, Einstein's principle of relativity, consequences of the special theory of relativity in regards to simultaneity and relativity of time, time dilation, the twin paradox, and length contraction.